And then I want to introduce Randy Hodges. I look forward to this every year because it's the only time that I'm really looking at the stars in this special way that I can't see with my eye. I don't know about you, but I can barely read this. So Randy is the chief docent at the local observatory here in Placerville. And we're excited to have him come today and tell us a little bit about what he's learned in this last year and share these amazing pictures of the sky. Randy.
Okay, Enigma machine. World War II was a way of sending a code to somebody so that they could read it, but nobody else could, okay? And all of these dials had to be set in exactly the right position, and if they were, you could type in a message and it would convert it into gibberish, and somebody on the other end could take that gibberish and set the dials in exactly the same position and read your message, okay? Very, very effective. Now, what happens if one of those dials was wrong? What do you get when you put your gibberish in? More gibberish, right? Had to be exactly perfect every single time. And it wasn't a matter of, it was almost right, okay? It had to be exactly right. And if it wasn't exactly right, all you got was gibberish. And actually, a lot of the reason why we won World War II is that we finally broke this code. It took a group of people, of Polish mathematicians and British mathematicians, who ultimately broke the Enigma code and figured out how to break it and figure out the messages that were being sent by the Germans, and we used that to sink a lot of their submarines and to help win the war. So anyway, why am I talking about this? Isn't this supposed to be about astronomy? And the answer is that that same principle applies to the cosmos. And the cosmos is a word that means the universe and logic and everything that we deal with. It's the sum total of everything. And for us to be here, for the cosmos, for the universe to have been created, everything had to be exactly perfect. It wasn't enough for it to be close to perfect. It had to be exactly perfect. And it's the same thing with this, except the difference is this only had several tens of thousands of combinations that you could pick. So if you were randomly try to push these dials in certain directions and decode it, you'd only have to try 10,000 times and eventually you'd get it. In the case of the universe, we're talking about way more than that. And the degree of precision necessary for the universe to exist is amazing. And that's what we're going to be talking about today. So let's go to the next slide. Some of you guys have heard of the name Stephen Hawking. And Stephen Hawking was kind of famous for who he was. And interesting guy, very, very probably thinking on the same level as Einstein. And he was in a wheelchair. He had MS, ALS, I guess, one of those, and could hardly speak. And he would sit in a dark room and think for like a month. And at the end of the month, he would bring somebody in who could understand him, and he would and talk, and hardly anybody else could understand him. And at the end, people would write it down and go, wow, this is awesome. And so anyway, Stephen Hawking gave us this quote, and I love it. It's great. He says, "The laws of science as we know them at present contain many fundamental numbers, like the size of the electron charge of the electron and the ratio of the masses of the proton and the electron." And then he goes on, and I put 3 dots there because it goes on and on. He's talking about specific things in science that have to be exactly right. He says, the remarkable fact is that the values of these numbers seem to have been very finely adjusted to make possible the development of life. Okay, so what does that mean? It means randomly, it's not going to happen, okay? And we're going to talk about this more in a little bit. But these factors had to be perfect. And the chances of them becoming perfect by chance are not possible. And we'll actually give you some illustrations of that later. And this argument is called the fine-tuned argument or the fine-tuning argument. And it's one of the strongest arguments that we as Christians or as we as God believers have to convince people that God made the world, because it just doesn't make sense any other way. Okay, if you try to argue with them about things, it's probably not going to work. But if you say, how do you explain the fact that the earth is exactly the right size, the atom is exactly the right size, the gravitational constant, and we'll talk about some of these things, are exactly right. So let's go in and let's get to the next slide. And these are some of the things that are exactly right. And in most cases, these, if they were off by a tiny fraction, like 1/1000th of a percent of the value that they have, we could not be here. Okay, so first is the gravitational force constant. That's how things in the universe connect to each other or pull on each other. Newton says that every object in the universe pulls on every other object, and the two factors that determine how much you get pulled are how heavy the objects are and how far away they are. So you're pulling on me, Dave, and I'm pulling on you. Hopefully I won't fall over. But not very much, because we're not all that massive. On the other hand, that is pretty massive, and that's the Earth. And the Earth is pulled by the sun, but the sun's a long ways away. And so all of those factors go into the expansion of the universe and the fact that we have orbits and things can exist. And again, if they were off by even 1/1000th, the universe would have either expanded uncontrollably or it would have fallen back on itself and never been here. So again, that's a requirement. The electromagnetic force, that's magnets. How much do magnets attract each other? The strong nuclear force and the weak nuclear force, those are the things that hold atoms together. If atoms don't stay together, guess what? We aren't here. And yet that is a requirement. And what's amazing is these things didn't have to be the values that they were. If things were created randomly, the chances of them having the exact values that they need to have for us to exist wouldn't be here. Okay, and anyway, I'm not going to go through all of these, but the velocity of light, the mass of a neutron compared to a proton, etc. All of these things are things that on a very basic level, if they don't work, we can't be here. Okay, it's kind of like this building couldn't be here if nails didn't work. You know, if you put a nail in and it immediately fell out, we wouldn't be inside a building. Okay, and these are the nails that hold the universe and hold us together, and they can only exist if they're those exact values. Okay, so next slide. These are just an explanation of some of those things. The gravitational force holds people on planets and holds planets, stars, and galaxies together. If it's too weak, the planets and stars can't form. Too strong, they burn up too quickly. And all of those things have to do, like the gravitational force has to do with how fast our sun is turning hydrogen into helium. And that's what we all depend on. All of life on Earth depends on that energy that's coming from the sun. And the amount of energy coming has to do with that gravitational constant. The electromagnetic force, strong and weak nuclear forces, I've already mentioned those. Okay, so let's go on. And this is important, the cosmological constant. And what we're talking today is there are people who spend their whole life with a piece of paper or a computer doing calculations. And they understand how things work, or they're trying to attempt to understand how things work. And one of the factors that they look at is this cosmological constant, the rate at which the attractive force of gravity with the repulsive force, and we, for example, right now, we don't understand what that repulsive force is. We just call it black energy or dark energy is pushing things away. But if it were too strong, we wouldn't have a universe. If it was too weak, everything would have collapsed back on itself. All of those things have to be there. And then this is important. If it were just slightly more positive or negative, the universe would fly apart. Slightly negative, the universe would collapse. And the degree of precision is 1 in 10 to the 120th. That's a number, if you're not a math person, doesn't make sense. If you take the number 1 and you put 120 zeros behind it, okay, that's how exact this number had to be for us to be here. Okay, now it doesn't make sense to us, but 120 zeros is a really big number, and one of those is very unlikely, okay? Or finding that exactly. The conditions at the beginning of the Big Bang had to be precisely right. Less than 1 in 230 parts different, and the universe could not have formed. And this is taking into account all the factors that make us up. And again, it isn't enough for one of those numbers to be right. They all had to be right. It would be like having 20 Enigma machines lined up here and me just asking you guys, okay, what number do you want? What number do you want? And we setting those randomly and they all working. Okay, what's the chances of that? What's the chance of even one of them working correctly by guessing? Very unlikely. Well, imagine that there were 20 in a row and you're trying to get all those. So very, very unlikely that those could have happened by accident. Okay, and then next slide. And there's a big word here, anthropic. Okay, anthropic. Anytime word you see anthro, what does that refer to? Humans, man, okay? So these are the things necessary for life to be there. Okay, and this is the list of anthropic properties, apparent accidents of a non-biological nature without which carbon-based and hence human life could not exist, is large and impressive. So when you start talking about the things that allow us to be here on this earth, it's a huge list. So let's go on and look at some of those things. One is the size of our moon. Our moon is unique. It is the biggest moon compared to the planet. Jupiter has some moons that are physically bigger, but they're tiny compared to Jupiter. Earth's moon is exactly the right size, and if it wasn't, the Earth's tilt would constantly change, and you think we have crazy weather now. You could imagine what it would be if we didn't have a constant tilt to our Earth. And it wouldn't be without the moon being there to stabilize our orbit and stabilize that. Okay, the next slide. These are just some other ones that are there, and I'm just going to pick a couple of them. Plate tectonics. The Earth is kind of, and we didn't discover this until like the 1960s, the inside of the Earth is fluid. It's liquid rock. Has about the consistency, think of toothpaste or something like that, or modeling clay. And it's moving around. Is that important? Yes, it is. What that does is that creates the magnetic field that protects us. And just in the last few months, we've had several aurora borealises. Have you guys heard of that? And I'll show you some pictures of it a little bit later. But those auroras are sending deadly particles from the sun without our magnetic field, which reaches out and pushes those out of our way, pushes them towards our poles and away from us. We would all have skin cancer all the time immediately, and we'd have to live underground. So that's just one example. The right amount of water in the crust and on the surface. How much water is on Earth? Anybody know? Almost 80% of the Earth is covered by water. Matter of fact, there's one picture that I love. It's a picture taken by a satellite over the South Pacific, and you can see no large landmass. You see a little bit of land just on the corners, but basically half of the Earth and the Pacific Ocean is covered by water. That's kind of a waste, right? Well, no, God knew what he was doing, and it's necessary. It's one of the things that make us what we are. That water moderates the temperatures on Earth. It allows weather to be predictable. It allows the highs to not get too high and the lows not to get too lows. It does all kinds of neat stuff for us. A large moon with its rotation, we talked about that. The right planetary mass. What if the Earth was a little bigger? Would that be okay? Probably not. Okay, we are just exactly the right size and less gravity. We know that people, when they go up in space, their body falls apart. They come back down and their eyes don't work correctly, and their blood is used to not having to work very hard, their heart, and so their heart is weakened. Their muscles are weak. We need the gravity that we have, and that protects us. And I love this one, and actually we'll talk about that later. Outside spiral arms of a galaxy. How many galaxies are there? They think there are 2 trillion galaxies, okay? And do you want me to repeat million, billion, trillion? I've done this before. Million seconds is 11 days, right? And when I'm doing groups of kids, I say, how many of you are a million seconds old? And 1 or 2 of them raise their hand. I said, no, you're all a million seconds old. How many of you are a billion seconds old? And all the kids raise their hand. I said, put your hands down. Because a billion seconds is 30 years. Think about the difference between 11 days and 30 years. That's a million versus a billion. And a trillion is 30,000 years. So when we talk about trillion, we're talking about a huge number. Well, they think there are 2 trillion galaxies out there. And for example, one of the most famous pictures, and I've shown this to you in the past, is called the Hubble Deep Field, where Hubble took a piece of sky the size of a grain of sand held on the end of your fingertip and focused on it for 10 days. And what did they find? Thousands of galaxies in that picture. And every direction you point, what are you going to find? Thousands of galaxies. If you repeat that experiment randomly throughout the sky, you're going to find thousands of galaxies there. And since we've got the James Webb, we found out even more. You know, that James Webb is a much better instrument than the Hubble Space Telescope, and we found out that there are thousands and thousands of more galaxies. And yet, most of those galaxies are unsuitable for life. Okay, most of those galaxies would not host us. Okay, if we were there, we couldn't be in those galaxies. And not only that, you have to be at the right place in the galaxy. Okay, if you're too close to the middle, there's all kinds of craziness going in there. Supernovas and neutron stars and all kinds of explosions that are ugly. Too far out, and we wouldn't have star formation and some of the things we need to survive. So being exactly in the right place is important. And the galactic habitable zone means there's a band of our galaxy is kind of like a flat frisbee, right? And the only place where life could exist is a relatively small area of that galaxy. And we're there, which is good. Okay, let's go to the next slide. And I love this one. Jupiter is the king of planets, right? Jupiter weighs twice as much as all the other planets added together. If you take all the planets, all the asteroids, all the comets, put them in a pile and weigh them, they weigh half as much as Jupiter. And yet, Jupiter is only less than 0.5% as big as the sun. But Jupiter turns out to be a very important reason why we can be here. Because Jupiter, having such a huge mass, means that it has a large gravitational field, right? And having a large gravitational field means it can reach out and grab stuff. Well, what's out there that it grabs that we're glad it did? Asteroids. And we think that Jupiter protects the Earth. It's in the position that asteroids that would normally hit Earth instead end up hitting Jupiter. And that is, again, one of the reasons that make us, and the term we use is a Goldilocks planet, okay? And a Goldilocks planet means everything is exactly right, okay, on this planet. So anyway, I love that. And maybe as many as 1,000 times as many asteroid collisions. And we know from Earth's history that we've had asteroid collisions in the far past, and they've been catastrophic. So, we're thankful for Jupiter, which is cool. Okay, next. And this is cool. I've seen this statistic, and I don't know who this guy is, but I'd like to be his friend. But the chances of us being here are less than the chances of winning the lottery 1,000 times in a row, buying only one ticket every time. Okay, think about that. What are your chances of winning the lottery? They're actually about equal even if you don't buy a ticket. But, very slim chance of winning anything. But you can imagine somebody lucky enough to win it 1,000 times in a row. Well, that's the chances of us being here. Very, very slim, very, very unlikely that we could be here if there wasn't some guiding principle, somebody who was tweaking those numbers for us and creating the world that we need, okay? And I think we have a pretty good concept of who that is. Okay, so next slide. Okay, and this is kind of cool. One of the questions we get all the time, we talk about how many stars there are in the Milky Way and how many galaxies there are and perhaps how many planets there are. We think there may be 1 trillion planets in the Milky Way. There's about 400 billion stars. Most of those stars, or many of those stars, have planets around them. So, what are the chances are there's other people out there like us? Okay, now, first of all, that assumes something that I don't assume, and that is that evolution is true and that the right conditions happen, that tadpoles will develop and ultimately they would become humans, okay? But let's accept that presupposition that they're going to do and talk about it for a little bit. I had a guy the other day, he says, how many millions of civilizations do you think are out there? And I said, I think we're alone. And he says, you're crazy. He says, there's billions of stars, billions and billions of galaxies. He says, no, there's several thousand billion galaxies. But anyway, what are the chances that we're alone? And this is actually a pretty neat statistic, and this is a scientist who did this. He says, what are the chances of being on the right size planet around the right type of star? Okay, out of the 1 trillion planets in the Milky Way, maybe only 1 billion of them have the right combination of star type and planet type and the right distance and all that. A stable climate for billions of years. What if we don't have a stable climate? Evolution couldn't occur, right? Life could not develop. And again, we're making that assumption that it's true. Okay, life must, and if that was true, that 1 billion planets, only 1 million of them would have those conditions, okay? Now, life starting is probably impossible from our point of view. We have no idea how it started. And they've tried to do it in the lab, they can't do it. But let's make an assumption that it's possible, okay? So life starting, that 1 million planets becomes 1,000. Complex life is very different. Okay, if all the planet has on it is bacteria or tadpoles, they're not going to be driving Teslas, right? And so it has to be complex life, and then if that's true, those 1,000 planets become one planet in the Milky Way. But what about sophisticated tool use? Okay, one planet in 1,000 galaxies. develop sophisticated mathematics and physics. You don't become what we are without those tools, right? One planet in 1,000,000 galaxies. Must be social creatures capable of discussing abstract concepts. One planet in 1,000,000,000 galaxies, and we must avoid disaster. And disaster, there's all kinds of ways we could get wiped out, right? Asteroids, we could blow ourselves up, we could invent some kind of pandemic that kills us all. That could happen too. So basically you have one planet in 1,000,000,000,000 galaxies. How many galaxies did I say there were? 2 trillion, right? So that means, assuming all those, and those are kind of optimistic, assuming all those are true, there might be another planet out there that has life on it somewhere in the cosmos. But chances are pretty good that we're alone. That interesting? And to understand that, you need to understand how unlikely it is that these things could happen by accident. Okay, they don't happen. They cannot happen by accident. Okay, next slide. And so the conclusion, if the current model of the origins are correct, we're alone. Okay, now, the ancients used to believe that the earth was the center of creation, right? That we were here and the sun went around us and the planets went around it and the stars were all pretty close to us. We know that's not true. Okay, what we do believe, and I honestly believe this, is that we are the center of God's creation. Okay, why did God make this huge thing and just in one little corner put us? I don't know. Maybe it was just to impress us. And it certainly impresses me. So when I see God's creation, when I look at the sky. So anyway, that's kind of my presentation. I kind of kept it simple tonight, but I want to show you some pictures, and then we'll answer some questions if you want. So anyway, these are some pictures we've taken at the observatory, and some of them are ones that I've taken that are individual pictures. And what I find is that when you start using big telescopes to look at the world or to look at things, you see stuff all the time that makes you go, thank you, God. That's amazing. And I honestly believe, and I think I've used this illustration with you before, that God hid things for us to discover that he knew we would enjoy, and I do that too. When I think about my grandkids, I think about, Tad is going to love this, and I buy it for him, but I don't give it to him till Christmas or something. Well, God has hidden a lot of stuff in the cosmos that we're just finally getting a view of, and the more we see, the more unlikely it seems that any of this could happen by accident. Okay? So anyway, this is kind of one of the most famous deep sky pictures. This is in the constellation Orion. Orion is the second most famous constellation. It's visible in the winter time. If you get up about 2 o'clock in the morning now, you can see it. But if you come back in a couple of months, it'll be in the evening sky. And this is a star-forming region. You see the little dots kind of in the center there? Those are stars that have just formed. And the gas and the dust are being pulled in by gravity and forming new stars. And the stars go through a process called a star-gas-star cycle, where they're pulled in, a bunch of gas is pulled in by gravity, it becomes a star, it lives out its life, and then it dies. And when it dies, it releases the gas again, either when it explodes or a process called a nebula, a planetary nebula, where it just shoots the gas out. And guess what happens to that gas? Becomes a new star. And that cycle is like cosmic recycling, and that happens. So anyway, this is a good example of that. Let's go to the next slide. This is two of my favorite galaxies. These are about 25 million light years away. That means the light we're seeing there left there 25 million years ago, and we're seeing it now. Is it possible they're not even there now? I suppose so, but we don't know exactly what is happening there now. This is what it looked like 25 million years ago. And occasionally we even see supernovas that occur in these galaxies. The one on the left is called the Cigar Galaxy, and the one on the right is called, and it's one where we're seeing it edge on. If we were to see it flat, it would look more like the other one. And the other one is called Bode's Galaxy, and those are up near the Big Dipper, okay, near Ursa Major. Those are two of the ones that are always visible, and I love those. Okay, next slide. Okay, this is the behemoth galaxy in our local group. Galaxies, there's zillion out there. They are in groups. They are in a group here, and then a group over here, and a group over here, and a group over here. They aren't evenly distributed. And we have about 22 galaxies that are in our neighborhood. Okay, when I say our neighborhood, you're not going to get to travel there in this lifetime anyway, but they are relatively close to us, and this is about 30 light years away, and it has probably 1 trillion stars in it. It's maybe 2.5 times as big as the Milky Way. And in this case, we're looking down on it, and this is a spiral galaxy. We know that the center of the galaxy probably has a black hole in it, and that's what's holding it together, and then these spiral arms contain stars, and new stars are being formed out in those outer arms of that galaxy. Okay, next slide. Okay, this is called Thor's helmet. Isn't that cool? And that is, again, another star-forming region. So not going to spend too much time on that. Let's go on. This is not a really good picture. I don't know why I picked that one. But this is the Andromeda Galaxy. Andromeda is the closest one to us. And you can see a galaxy above it and another galaxy below it. And I kind of like that. This is about, again, close to 1 trillion stars. It's about 2.5 million miles away. Not miles, light years. By the way, do you guys understand the term light years? Let me just digress for a second. You're used to the idea of using time to indicate distance, right? So if I tell you, how far away is Sacramento? Some of you say, 45 minutes. Okay, well, is a minute a distance? But you all know what I'm talking about, right? Because you know that we normally drive cars, and a car goes so many miles per hour, and it takes 45 minutes to get there. How far is Los Angeles? Well, 5 hours if my dad is driving, 8 hours if mom is driving. So we're used to that concept. Well, in this case, we're using the speed of light as our measurement and talking about how far it travels in a certain amount of time. So for example, the moon is just a little over a second away for light to go from Earth to the moon. And we do that regularly. We have lasers that we shine on the moon and measure its distance. And when we were there on the Apollo program, we left a thing called a retroreflector on the surface. And a retroreflector, when you hit it with a laser, it shoots the laser straight back at you. And we're still using that, which is kind of proof that we actually got there. Somehow or another, it's up there. But of course, the people who are crazy would say, NASA's just faking that too. So anyway, this is about 2.5 million light years away, and they think in about 3 billion years, it and the Milky Way are going to merge into one galaxy, which is pretty freaky. Start building your shelter now. Okay, next slide. This is called the Leo triplet. So those are 3 galaxies, and what I love about these is they're all at different angles. Like this one on the right, you're seeing it edge on, and do you see the dark? That dark is what they call soot or dark matter, or not dark matter, but a dark nebula, and that's blocking it out. And when you look up, if you ever look up at the Milky Way at night, does it look uniform? No, it's got patches in it. Well, the reason why it has patches is because it has those dark nebula that's blocking our way to seeing those stars in our own Milky Way. So anyway, that's a good one. Okay, next one. And that one, anybody know what that one is? Okay, that's called the Seven Sisters, or the Pleiades, or Subaru. How many of you have a Subaru? Okay, well, that's on the back of your car, that same constellation, a group of stars. And this is a young star-forming region. Those are relatively young stars. Okay, so that's a good one. Okay, next. Okay, and this is called the Flaming Star Nebula. Is that cool? And that's, again, a very rich nebula area, and this is what they call an emission nebula. It's glowing because the stars near it are exciting the gas, similar to the way a fluorescent light works. A fluorescent light, electricity excites that gas and it lets off light. Well, in this case, the stars near it are doing that with this gas. Okay, next one. Okay, this is one I love. This is called the North American Nebula because to somebody that looks kind of like the Gulf of Mexico and the west coast of Mexico, and didn't do really good with the east coast of Mexico. But anyway, a wider picture, it looks somewhat like North America. Anyway, but this again is a very rich section. Look how dense those stars are up near the top. This is in the path of the Milky Way itself. Okay, next. Okay, and this is what you get when you start looking towards the center of the Milky Way. Okay, how many stars are there? 7, 9, maybe 1,000. And it's pretty freaky to realize that every one of those stars could have a solar system, it could be amazingly complex. And the other thing is those are trillions of miles apart. They look like they're really close together to us, but in reality, they're very, very distant from each other. They're just so far away that they look very, very crowded. Okay, so next. And this is cool. This is the fate of our sun. Okay, our sun, remember, is really big. We think it's about 5 billion years old, and we think it'll live about another 5 billion years before it goes into its death cycle. And its death cycle is it runs out of fuel. Every second, our sun burns about 490,000 tons of hydrogen and turns it into helium. And when it does that, the helium has a little less mass than the hydrogen had. And what happens to that mass? It gets turned into energy, E equals mc squared. And that 4,000 tons of mass that is lost becomes energy, and that energy is sent to us. Well, at some point, our sun's going to run out of fuel. And when that happens, it will bloat up and become what's called a red giant. And that red giant is so big that it actually will encompass the Earth. It will go all the way up. And when that happens, the outer atmosphere or the outer edge of the sun is so far away from the center of mass that it isn't being held on to very, very vigorously, and it'll get pushed out into a bubble. And that's what this is. It's a bubble. This is called the Dumbbell Nebula, and with kids we call it the apple core. But that is a star, and you can kind of see the star in the middle that is going through that death process and blowing up into what's called a planetary nebula. And they call it a planetary nebula because originally people seeing it without really good telescopes looked at it and said, oh, that looks like a planet. But of course we know now it doesn't have anything to do with the planet, but the name stuck. Okay, next. Okay, another galaxy. And that one is called the Black Eye Galaxy. Okay, next. Another galaxy. Okay, I'm going to go through these pretty quickly. Okay, this is one I like. This is called the Trifid Nebula. That's pointing towards the center of the Milky Way. And it has three kinds of nebulas there. The red is one of those emission nebulas I told you about. The black is one of those dark nebulas. And do you see the blue off to the left? That blue is a reflection nebula. That's a light reflecting off of another galaxy. So that's kind of a fun one to look at. Next, what I want to talk about is just some of the exciting things we've done at the observatory this year. We are very unique in that we have an observatory. Most communities do not. There's only one other in California that's anything like this, and that's in Chico, and they only meet about once a month. But we meet every Friday and Saturday night. We've seen 12,000 people already this year have visited the observatory, and we have about $750,000 worth of equipment that we regularly use and show some people some amazing stuff. And one of the things we did this year, okay, actually, we'll talk about this one. Stop here for a second. We the sky is always doing amazing stuff. And on May 7th, the sun, which isn't this placid, nice, calm thing, is an exciting, vigorous thing that's going crazy, spat out a whole bunch of charged particles in our direction. It's called a CME, a coronal mass ejection. That'll be on the test. Make sure you know that. A coronal mass ejection normally doesn't come our direction, but on that day it did. And it hit the Earth on Friday night, May 10th. And on Friday night, May 10th, about 9 o'clock or 9:30 at night, this is what we saw from the observatory. And there's our bathrooms off to our right there. But we had about 400 people up there to see it. And that is the Northern Lights. Now, to the naked eye, you didn't see all those colors. That was done through my phone, okay? And the phone can pick up colors that your eyes can't, okay? In the dim light. But those are the real colors that were there. And just interestingly enough, the TV stations heard about it and sent a team up, and they filmed and interviewed us and everything. The next night, we had 2,000 people show up, but you know what didn't show up? Oh, no aurora. Okay, is that ready to go? Okay. Okay, this happened in April, so sit back and enjoy. This is in April 8th, we had the best solar eclipse in many, many years that came up. And we were in Illinois with about 80 people observing it. And this is a 3-hour or an hour and a half time lapse here of the moon crossing the face of the sun. And where we were, the moon completely covered the sun for about 4 minutes and 3 seconds. And I want you to watch how it darkens here. And if you listen carefully, you can hear even the crickets came out when it got dark. And it dropped 16 degrees. It was 84 degrees when we started and 68 degrees during the full eclipse. And anyway, notice how dark it's getting there. And then this is the countdown to totality. And those are my grandkids that are going crazy. And this is what we saw. That's called the diamond ring. It's the last little bit of the sun peeking out from the edge. And then this is what we saw during totality. Okay, pretty amazing thing. We're the only planet where that can happen. And do you see on the bottom there are some flames, it looks like? Those are called prominences. That's where material is being spat out from the sun but being pulled back into the sun. And that lasted for about 4 minutes. And it went by surprisingly fast, but pretty amazing. And that's called the sun's corona that you're seeing, and you can only see that during an eclipse. And then it came back, sadly. And this took another hour and a half for the moon to recede from the sun. And there we were. Cool. So anyway, that's an example of something that we do at the observatory. You guys want to know what the bad news is? The next eclipse to hit North America is 20 years from now. So probably not going to get to see that, some of us. Anyway, if you're willing to travel, there's one that hits somewhere on Earth every couple of years. So, for example, the next one, and we may get to go with this, my wife and I, is in Iceland, and it's in 2026. And in 2027, there's one that goes through Gibraltar, all the way across the northern end of Africa, and through the Valley of Kings, where the pyramids are. And that'll be over 5 minutes long, so that would be amazing. So if you have a couple $10,000 extra, you may want to book that. But anyway, very emotional experience to see what a wonderful thing those eclipses are. Okay, and the last thing I'm going to show you, and then I'm done, thank goodness, is this is just a week ago, and actually it's happening right now. There is a comet visible in the sky. And the one on the left was, again, me just holding my phone up and taking a picture with my cell phone. Nothing fancy going on, no settings that were changed or anything. And that is the comet. And the comet is called, and this will be on the test too, it's C2023A3 Tushinshan Atlas. You got that? It was discovered by a Chinese guy and an automated observatory in South Africa. Anyway, that's what it looked like to the naked eye. Actually, it wasn't as bright as that to the naked eye, but you could still see it. And then on the right, and that's what it looked like in a telescope. So pretty amazing. And comets are amazing things. And only about once a generation does a comet this bright come around. And some of you guys probably, how many of you saw Halley's? Okay, you probably call it Haley, right? Okay, it's Halley. But I was in Great Britain. I was in London last year, and I visited the Royal Observatory, where he was one of the astronomer royals. And if you say Haley, they slap your hand. That's not true. But anyway, he did call himself Halley instead of Haley. And that came in 1986. The next one, Halley will come back again in 2061. So I'm probably not going to be there. Some of you may, but we'll see. But anyway, comets are pretty amazing. And like I say, a great one only comes around every 20 years or so. And this was a pretty good one. It wasn't a great one, but it was a pretty good one. So anyway, that's pretty amazing. So anyway, a couple of quick things. I want to advertise the observatory. The observatory is free. You do have to pay $2 to the college for parking because we use their parking lot. And we're open every Friday and Saturday night during the wintertime, 7:30 to 9:30. But we're in the process of arranging a time when you guys can come up just by yourselves. And you won't be fighting the public. It'll just be us. And we will announce that later. Cheryl will be able to announce that for you. Okay, so it's already 2 o'clock, so it's probably time to go, I would guess. Do you want me to just hang around and answer questions? Or do you want me to answer questions as a group? Okay, I'll just hang around. So anybody has questions, want to talk to me, I'll be happy to do that, but thank you very much.